Hello students. Now today what you see on your screen are three learning objectives which come from the chapter of dual nature of radiation and matter. So we would like to discuss this interesting aspect because you all are very well informed nowadays, because a lot of study material and information is available at your fingertips. You know that Einstein was given Nobel Prize for this particular phenomena of photoelectric effect. But we will have to go into slightly deeper from what Einstein did. Work on this photoelectric effect. But talking about dual nature of radiation, and then Hertz and Leonard's observations, which are also of primary concern to this topic of dual nature. So let us not stick to these and move a little forward. What was interesting at some point of time in 19th century is that a lot of studies were done at macroscopic world. So in 19th century, Newton and Maxwell, apart from many others, were able to provide a lot of studies in the macroscopic world. The macroscopic world as we see it, small objects moving around all in this world, and whatever are the laws applicable, they were actually given by Newton's. And the transmission of energy in the form of wave was one of the main areas of study of Maxwell. So this was known as classical mechanics. This was the world of classical mechanics, where a lot of basic laws, fundamental laws, were applicable to big objects and the propagation of energy through atmosphere or through space in terms of waves. So sound waves, electromagnetic waves, and so on. On the basis of these theories, many physical events were explained. For example, what will be the force on two bodies if they collide, what will be the change in the momentum, what will be the velocity and acceleration and force experienced, then related to exchange of momentum, then impacts and all that. Apart from it, waves were basically, the studies were restricted to sound waves and electromagnetic waves, and it was assumed that wave is nothing but something which takes along energy with it, and the phenomena of mainly produced by light, for example reflection, refraction, diffraction, all these phenomena, polarization, all these were the phenomena which were explained by Maxwell, and this entire study of physics which was going on in the 19th century was known as classical mechanics. But what happened later on, as this new science developed, which many scientists called it as modern physics, as a new science developed, more and more studies were done on microscopic particles. The microscopic particles are some of the fundamental particles as we knew at that time were electron, proton, neutron, and all that. So you know that under the influence of electric field, a cathode ray tube starts ejecting some small particles, and there was one name which became prominent, is that of Jean Perrin, and later on there was another name, J.J. Thomson, who you will recall through cathode ray tube gave the calculation of the ratio of charge and mass, E/m ratio. It was given by Thomson, and then Millikan was another scientist who studied the microscopic particle electron, and he was able to find out the charge on electron. And when charge of electron was found out, then since this ratio was already known, mass of electron was also known. So the point here is, a lot of all these scientists started talking about minor particles, small particles. So in a way, it was observed that microscopic particles do not behave in the same way as macroscopic bodies. Many scientists started realizing that some of the properties in the microscopic world were not behaving the same way as macroscopic bodies. And there were a lot of studies in the field of radiation, in which they found that the energy which is given out by certain bodies show a particular maximum energy at a particular wavelength. And since wavelength is directly related to frequency, so more the wavelength, lesser is the frequency, and vice versa. So they were able to understand that lot of objects which had energy and which were radiating out energy were giving out maximum intense energy at certain frequencies. And from there, the entire development of Planck's theory developed. Now Planck said that he was studying black body radiations, and he was able to study that if energy is understood or energy is measured for particles which are very small, then the energy of the small body, in this case a particle, depends on the frequency. More the frequency, more will be the energy of that particular particle. Now, this was in contrast to the classical mechanics theory, in which the energy of the oscillating body was in a way measured in terms of its amplitude. You will recall that in simple pendulum, the energy of the simple pendulum is directly proportional to the square of the amplitude. But here, for a small particle, amplitude didn't matter, but the frequency mattered. And therefore, all these studies, which started from Jean Perrin and Thomson and Millikan and Planck, Max Planck, there was another scientist who started this entire discussion, Max Planck. They all came to the conclusion that for smaller particles, if we talk about the energy, then it is directly proportional to its frequency. It is directly proportional to the frequency. So energy is directly proportional to the frequency. This was studied, and it was one of the most, I will say, influential feature of changing the perception of the scientists from classical mechanics to something called quantum mechanics. So they started realizing that the classical world, which we see in day-to-day life, and the quantum world, which is the world of small particles, the behavior of these two worlds are not same. So there is a huge difference. And from there, lot of studies went into the discussion of how these things are to be studied more and more. So in the next stage, many scientists started discussing about how to understand this entire world of macroscopic, from macroscopic to microscopic. So Hertz was one of the pioneer, Henrik Hertz, here, and so we will have to discuss about him. Henrik Hertz, what he did, he took this type of a tube. I am drawing the tube so you can clearly see it. He took a evacuated tube, a glass tube, and there was a cathode, and this cathode was connected to a battery and given a negative potential, as you can see. And then there was this anode. There was this milliampere ammeter over here, and then it was connected to the positive. So in a way, this plate was positive and this was negative. And he started discussing the discharge. You all know that in cathode ray tube, when the negative potential of the cathode is kept on increasing, then after a while it gets heated up and there are certain particles which come out, and those were the cathode rays, and cathode rays are nothing but stream of electrons. But Henrik Hertz studied this in 1887, and he found that if UV radiation falls on it, then the effect of coming out of the electrons is highly pronounced. Do you understand what is the meaning? The meaning is, suppose earlier there were two particles or two electrons coming out. When UV radiations were falling in this particular apparatus, then the number of electrons suddenly increased, and therefore this was recorded by this milliammeter. And he was actually not able to explain why it was happening. But many other scientists, since this was the new science at that time, lot of energy was there among scientists to talk about something in the microscopic world. So they all started discussing this entire phenomena, and they came out with certain conclusions. The conclusion is that if radiation is falling on it, it provides the energy to some more electrons, and those electrons absorb that energy and they are able to come out. So some energy was being provided from the radiation to the electrons. So there has to be something which was acting one-to-one, right? Some energy is coming, that is being absorbed, and it is coming out. Electron is coming out. So there was one-to-one correspondence between energy of UV radiation and electrons being ejected. This was the beginning of what is known as the photoelectric effect. Although I will say, and it is known that Hertz was not able to explain it fully. So photoelectric effect. This was the beginning. This was the beginning rather. So this was one of the observations of Hertz. So it was just the observation. Right? After this, Leonard did another observation with another set of instrument, and that is slightly different than what Hertz did. He took a zinc plate, and this was Leonard observations. In Leonard's observation, what he took is a zinc plate, and this zinc plate was connected to an electroscope. And ultraviolet radiations were incident on the zinc plate. And electrons were ejected, and the plate kept on becoming positive and positive, and therefore these two leaves, gold leaves, this was gold leaf, electroscope, and the gold leaves started moving away from each other, and it meant that it is getting charged, right? Because since it was connected to the zinc plate and earlier it was not charged, and if the gold leaves started moving away from each other, that means it is acquiring charge. In comparison to Hertz experiment and cathode ray tube experiment of J.J. Thomson and Jean Perrin, it was understood that if light rays are falling, then electrons are coming out. So if electrons are coming out, then the gold leaf electroscope experiment was valid. It was valid because it was getting charged, and this plate was getting positively charged. And to maintain its neutrality, because electrons are being ejected out, so more and more electrons are being supplied from this metal to the zinc, and that is why this becomes more and more positive. So Leonard was able to explain that particles are coming out from the zinc plate if UV radiation is falling. That is, if light is falling, then particles are being ejected out, which in addition to what Henrik Hertz said, that This is a new phenomena in which small particles are absorbing energy from the light radiations and they are coming out from the metal plate. So this was the beginning of the photoelectric effect. After it, a lot of scientists started studying it, and Albert Einstein was one of the pioneers in this field, and he was able to propound certain laws. So what we are going to do now is to look at one of the activities or animations which can tell you exactly how it looks like in these type of observations which Henrik Hertz and Leonard and others did. So I hope you are able to look at this. There is a battery over here. That you can see at the bottom of this picture. The current will be measured by this yellow rectangle which you see. This plate can be made to be negative and this plate can be made to be positive. There is a light which just an extension of some light radiation whose intensity can be varied. So I want to increase it to 100%, and we have an option of zinc also here. And I will keep it slightly on a negative. See what is happening in this particular value. So you see, if you read out there are 298 nanometer of UV light at around 3 or 4 volt. This side is positive, this side is negative, and if I start reducing it to 284, suddenly electrons come out, and if I make it to around maybe 224 nanometer, you can see lot of electrons are actually coming out, and the current is 0.188 ammeter at 4 volt. Now if I reduce the intensity, see what happens. If I reduce the intensity, you see the current is changing and it has gone down to 0.057, and if I just stop the light, nothing is happening. Nothing is happening even if this plate is negative and this plate is positive. There is no discharge, there are no electrons coming out. So if I increase the intensity of the light, and I see particles coming out. So even at 10% of the intensity, some of the light is coming out, some of the electrons are coming out, and which is constituting an electric current. So if the intensity of the light is reduced to 0, nothing happens. But if it is some intense light at a certain potential and certain wavelength, then there is a flow of current. So this gives a clear picture that light incident on a cathode which is already at a negative potential will give out electrons, and that will constitute certain amount of current. So this is an animation which helps in our understanding that depending on the intensity, the value of the current changes through the cathode ray tube. So I hope that you have understood the basic concept, why there was a need of this quantum mechanics. Not necessarily the need, but this was just a development from classical to quantum. And then there were many studies, the schematic pictorial representation of what Hertz did and what Leonard did. What is actually the photoelectric effect? We can always talk about that and the definition of that, and a small activity which gave you a rough picture of the potentials and the current and the intensity as well as the wavelength of the light. So here you can see that at 4 volt, 0.066 current is passing through at 224 nanometer of UV light at an intensity of 35%. And all these variables can be changed, and you can experiment with this animation and see how the values keep on changing.